We are going to do bare metal programming. So we are going to manipulate the registers directly to do our work. We're not going to use HAL. Okay.
We are going to use HAL.
See this? Okay. Okay. For now.
Yeah. For now, yeah. So I have the LED green configured with a GPIO as an output in push-pull mode. What else? We can take a look at the clock configuration. So initially, it can look, a little bit daunting if you this is if you're not familiar with clocks. For H7 and higher end MPUs, this is much more complex. I think for F4, it is a little simpler. So the clock, I just want to ponder over it for a couple of minutes. Clock is like a heartbeat for our microcontroller chip. So so our MCU is a synchronous machine. So it doesn't have a you know idea of time. So if we do our talking and we tell each other that okay, meet me at 10, or join the seminar at 11, so we both of us have clock which we can refer to, but different peripherals and CPU doesn't have any clock. Like the watch that we have, they have this clock signal. The clock is a square wave signal, and it is used to synchronize between memory peripherals and the CPU. This clock can be generated with different sources. So ST provides different kind of sources from which these clocks can be generated. So we have a high-speed external oscillator, we have high-speed internal oscillator, we have low-speed external, we have low-speed internal oscillators. So these different kind of oscillators that I'm talking about, the external oscillators are somewhat that are on your board. So if you see your board, you can maybe find one oscillator by the name X2. So it is a external low speed external oscillator. So the advantage of using an external oscillator is you will get a higher accuracy. So whatever you can see here on my cursor, the input frequency 32.768. This is a low speed external oscillator, and this is used in RTC real-time clocks because this is somewhat one of the most accurate oscillators. So we prefer using this oscillator as our and it is low speed as an input to our RTC. There is one internal oscillators, the LSI. So this is an oscillator that is manufactured. This is actually a crystal, and this is actually electronic circuits that are generating this frequency of 32 kilohertz. There is this high-speed internal oscillator that is creating a frequency of 16 megahertz. The low speeds are in the range of kilohertz, and the high speed is in the range of megahertz. And we have an external high-speed oscillator as well. Okay, so first of all, we want to select which oscillator, what is the source of the clock we want, what oscillator we want as a source of our system clock. So system clock is the clock which synchronizes the CPU and the memory and the bus AHV AXI bridges. So we want to get the source of the system clock here. Here there is a mux, and we can select which oscillator it is. So we are currently using here for LSI for our RTC. This is gray because we have not enabled RTC and we will not do it today. Coming here, okay. So we have two options, HSI, HSE and HSI. We have the option to select HSI, not HSE. This is, we can change it, but this is true. Why? Because we don't have the HSE connected on our board. So if you look on your schematic, I can show you here in the schematic, but you can look on your board, then the oscillators are named by X. So X3 here is an oscillator. It is shown in the schematic, but it is not present on your board. You need to connect it by yourself. However, whatever frequency oscillator you want, you can connect it and solder it on your board. The X3 connector, it is open, you can see on your board. So we cannot, if you have not connected it manually, we cannot use the high-speed oscillator in our clock configuration. So we have the internal oscillators. The advantage of external oscillators are they are more accurate, but they they have a high startup time, but the high-speed external oscillators have low startup time, but they are less accurate. So we have chosen the high-speed internal oscillator. My bad. Then we are providing it to a PLL. So the PLL is a phase locked loop. You can find two kind of circuitry here. One is a PLL and one is a prescaler. So PLL is a circuitry that you use in order to amplify your frequency. So we are inputting, for example, here the frequency of 16 megahertz, and we are multiplying it by a factor of 336, dividing it by a factor of 4, and we are getting an frequency of 84 megahertz for our system clock. So you can use these different multipliers in order to increase your system clock frequency. So, and you can use these dividers, the prescaler, in order to divide your frequency by a multiple of 1, 2, 4, 8 by any power of 2. And you can see how this. So we can directly use the HSI as our system clock. That way, we will have a system clock of 60 megahertz, or we can use the PLL, and we can have the system clock of 84 megahertz. So this is something you can configure in the CubeMX tool. This gives you a flexibility so that you can adjust your frequency. For example, I want to give a clock of 36 megahertz to APB1 peripheral clock, and the tool will automatically modify all the parameters before, so that you get the desired frequency here. So, and then you can generate that code as per that. And if it is not possible to get that particular frequency, for example, you cannot get 35 here, maybe you can get 32 here. So it will tell, okay, this configuration is not possible. You can try another one, and then the desired frequency range you can mention, and it will give a thumbs up. Okay, this configuration is okay. You can generate a code for this. There is a MCO. The MCOs are microcontroller outputs, MCO1 and MCO2. So whatever frequencies that we are generating, we can enable this MCO pins, and then we will be able to select which clock frequency we want as an output. So these are some GPIO pins that are on your board, and we can take output these clock frequencies, and we can measure the frequency of that particular clock. So This is helpful in debugging. For example, you did your configuration for sys clock to be 84 megahertz, but your system is behaving weirdly. You want to check, is actually my system clock is 84 megahertz or not. You can take the system clock as an output from the MCU pin and measure it in an oscilloscope. And it is also helpful if any external circuitry is dependent on clock. So if it wants to be in synchronous with some circuit, peripheral in your board, then you can take the clock output from here and give it to that particular circuitry. So it is helpful in some debugging purposes and other purposes. Okay, so we will generate our code. Now I will save it. If you want to generate code, yes. So this is an Eclipse-based IDE. We will have different perspectives. So there will be the debug perspective. There will be this QMX perspective. So okay, if you want to switch the perspective, just remember my decision and yes. Okay, so we have the code generated.
So we can also use this MCU O2 output, basically the clock of the one board, and give that same clock to another board by connecting the MCU O2 output to the other board's pin, right? And we can do the same thing, right?
Yeah. Yeah. So we have the code generated here. What files do we have if we take a look into it? We have the includes mentioned here. So whatever the included files, the files it includes. We have a folder named core. It will have the application include files, the source files. This is the startup code. And we have the drivers here. So these are the drivers that are provided by ST. And this is the application code. So your application code will be here in the source main.c and it.c. All this is application code. This is drivers. Let's start with the main.c. Actually, before main.c, let me cover the startup code. What is the startup code? Let me show you. So when this project is generated, the startup code is generated. The startup code is toolchain specific, and it is provided by ST. It is majorly a assembly file. And what we do in the startup code is, first, whenever there is a reset, our code, the flow of the code, it will come to the reset handler function in the startup code. So the reset handler, first of all, it initializes the stack pointer. Because we want to go from here to our main application code, and the main application code is nothing but a function, the main function, and it will require stack area in order to insert its variables and the local variables parameters. So we need to have initialized before we call the main. So this is initializing stack pointer with this symbol end of stack. These are some of the symbols that we define in our linker file. Then we go to system initialization. So system initialization is a function which initializes some core registers that are required in order to function correctly. If there is a FPU unit, we want to use that floating point unit. We want to initialize some registers here, and if we want to configure the vector table location, the we have a vector table offset reset register in the SCB block, so we can adjust that as well. So some low level initialization that we want to do in system init. Then we copy the data. So if you know the memory layout of a C program, we have dot data section, BSS section. So we copy the dot data section from flash to our RAM. So when we initialize any data, we have some literals, the constant literals that are stored in the data section in the flash, and we want to execute the code. We want to we can change the data, so it cannot be in the flash, so we need to copy it to the RAM. So this just copies the data, and it fills the BSS section with 0. So BSS sections are like static and global static variables which are not initialized, static and global variables which are not initialized, and they are by default initialized by 0. So it just fills it with 0, and then we branch to the main function. So here we go to the main function function. So in the main function, we are initializing HAL. HAL initialization basically it does a sysdig initialization. So this sysdig is a timer that we require for HAL delay. You can I will give you this information as of now because it will be too deep. We need to cover different things. So as of now, you want to know that sysdig is something we want to initialize if you want to use the HAL delay. So this is the function which initializes it, and you can do different initialization on this in this function. Then this is configuring our system clock. So this is the code generated by our clock configuration tab. Whatever I showed you in that CubeMX tab, the clock configuration tab, here is the code generated for it. So if you can see, the oscillator type is HSI. We have chosen the HSI, and we have chose the PLL. So all these configuration are done here in this part of the code. So everything we chose, it goes into a structure field of RCC that is defined in RCC module, and then we call the function called oscillator config, HAL RCC oscillator config. Then after configuring which source we want as for our system clock, we want to set the clock frequency. So this is done by the clock config function. You don't need to worry about it as of now. This is taken care of by the tool. After the system clock configuration, this is the code that is generated by the CubeMX, that is MX GPIO init. If we go into that function, what it does is it is defining a structure of the variable type. The structure type is GPIO init tab def. So we have different parameters. What we want to do is to enable the clock of the GPIO. So everything that is present on this chip need to be, if we want to use it, the peripherals, if you want to use it, you want to enable its clock first, because everything is clock gated. We don't want to waste any power if we are not using the peripheral. So if you want to use the peripheral, you enable its clock and then use it. And then if you are done using it, you deinitialize it, and in that deinitialization you disable its clock so that you don't lose any power unnecessarily. So if you want to use a port, that is the GPIO pin PA5, we want to enable its clock first. So these are the APIs that are provided by the HAL the RCC module, and they do enable the clock of the A port. So after enabling its clock, I want to make it low. So this is okay. This is low. Make it by default reset it. Then we want to configure it. For configuration, first the pin is GPIO green pin. If you remember, this is a user label I mentioned in my CubeMX project. So this is nothing but a uh, macro that is defined in my main.h. The GPIO green pin is GPIO pin 5, and the port is GPIO A. So we use this kind of method so that in future, if I am using this LED, if I want to switch the pin for my LED, or if I want to use different LED, if I define it with just the LED, I can switch my LED just by modifying this piece of code. And I can skip modifying my code all over the main.c file or my application code. So this is a good programming practice. So whatever we did in our CubeMX tool, the same configuration is done here, and then we call the GPIO init function. So our LED is now initialized. Now we want to use that LED in order to blink. Sorry, the GPIO is initialized. We want to use that GPIO to blink our LED. So we have a while one loop here. What I will do is I will call a GPIO function. So if you want to call any GPIO function that is a HAL, that is a HAL function, you need to start with HAL. Then the module name, I want to call the GPIO function, the HAL GPIO. Then you can just press Control Space. So what the control space does is it will show you what the APIs you have, whatever the APIs that are exposed to you, you can use them. These are you can use them in order in your application. So it will give you a list of what is available. So we want the toggle pin. We want to toggle it. So I will just click enter here. The first parameter that you want to give is a GPIO pointer. So this is the GPIO you want to GPIO port actually you want to give here. So these are named by GPIO A port, etc. But we have used a defined for it. We have LED green port, and that is a GPIO A. So I will use this macro, and the pin is LED green pin. Okay, so this will toggle the LED, but we want to give some delay so that I can see it blinking. Again, control space, I got the delay function. So the delay in the hard delay is expressed in milliseconds. So if I give 500, it will be half a second. Save it. I will just quickly check it.c if we have the sysdig defined. Okay, so we have the sysdig defined, so our HAL delay will be working. This, so the code is ready. I want to build it. So these are different kind of build configurations. I have two build configurations here, debug and release. What I want to do is, now why we have these different configurations is, you want to, for example, in different configurations, you want to, exclude a piece of code and include some other piece of code. This we do it by defining some macros, the if compilation macros that we use. So the different configurations, they differ by uh, these settings here. So you go to any project, right click on it, go to properties, and go to C++, C++ build and settings. So this is the main tab. You want to come here for your configurations. So here you can see different configurations are there, and here are is the list. So generally, uh, if you click on here, you will get which board you have, F401RE, CPU, all these instruction, all these things, the instruction set, if you want thumb 2 or ARM instructions. Anyway, whatever you want, you can choose. Then we have the compiler. The compiler have some preprocessors. What these preprocessors are, these are some kind of macros. So when we are compiling our code, these are defined with the symbol -d. So it is just like we are defining it in our code with with the hash define symbol. So if I use in the code hash define debug, it will be it is just like that. So I can list my macros which I want to enable, in my code here. So this in this preprocessor tab. So if I see it for the release tab, this one, all release tab, there is no macro called debug. So these this is how the different configurations differ from each other. Okay. The debug configuration, it when we go to the debugging, so it will halt at the main, but in in release it will just directly run it your code. So this is the difference between these two configurations. We have include paths, from where we want to include the dot and the header files. So you can list all your header file paths here. We have the linker. So the linker path is shown here. So it is the workspace where you have a .ld file. I will show you. And the different parameters, if you want to generate a map file or not, if you want to discard the unused sections or not. So these kind of different settings you can do here. For now, I want to build my code. So I'll just go debug. And it will build my code. So the code is built. If you see these logs, these are nothing. It is just executing a make file. So all whatever the configurations we did, it just made a make file. So this is the make file that it created. It created it automatically, and it just executed the make file. and you can see each file is compiled with this GCC compiler, Amnan EABI GCC. And this is the file name, the C file we want to compile. Then these are different options we did gave, and you can see the preprocessor symbols that we defined in the library are defined here with the dash D symbol. So these macros are defined. Uh, then the includes are shown. Everything you can just take a look in your PC. So everything will be given it as a make file. This is automatically generated. You should not edit it. So this is a good way so that by which you can compile your code easily. Now, whenever you build, there will be a folder created in your project explorer by the name of the configuration. So if you have debug and release, if I click on release as well, there will be a folder by the name release. So what the debug and release folder, they will have all the binaries and the ELF files and the map files that are created for these source files. So you can, if you don't want to clean it, you can just delete it. These folders you can delete it. These are binaries. You can create it again. Okay, so we have the binaries created. Now I want to debug. I want to dump the code on my MCU. So sometimes what happens is if your board is new and if you have not worked on it for a while, your cube ID won't uh, you know won't be compatible for your ST link that is attached on your board. So if you have the board, there are two parts on the board. One is ST link and one is your main MCU board. The ST link is an interface between your PC and your MCU. You can say it like that. And it's a debug probe by ST. You need to upgrade its firmware if you are not able to identify any ST-Links device connected to your PC. So just click on help on your cube ID and click on ST-Link upgrade. Yeah, so I have the ST-Link upgrade. Click on open in update mode and click on upgrade. So your firmware for the ST-Link will be upgraded through these steps. Okay. So my ST-Link firmware is upgraded already. I won't do it. Now what we want to do is just like the build configuration, I want to create a debug configuration as well. So I will click on my project debug as STM32 application. So this window will be open. You can see your ELF file, which binary you want to debug. So this is in the debug folder because we want to run this ELF file that is present in the debug folder. And in the debugger tab, you will have the port number on which the GDB server will be hosted. I want the interface to be SWD. So there are different kind of interfaces, JTAG or serial wide debug, which you can use. So different the ST link. If you want, if you have two different ST links, connected, then you can click on this shared ST link button and all the ST links that are connected on your PC will be listed here. And then you can choose and the ST link that on which you want to dump this code. If I go to startup tab, here I want to give two initialization commands. So what how we run this GDB server is through OpenOCD. So uh, the OpenOCD takes in commands through uh, a mon prefix. So we want to give mon reset and mon halt as the two commands to our OpenOCD server, so that it resets our board and then halts at main.c. So this is the two commands we want to give, and give apply and OK. It's taking some time. You can see the launch here on the right side. So my debug session has started. It's taking some time. Okay, so yeah, we are here. We are on the first line of the main function. We have a breakpoint here. Now, either you can give a free run, or you can step into, step over all these debug features you can use. You have the variable expression window here. You have all the registers, the SFRs, all the registers are here. You can take a look into it, what values are written down on these registers. So you can just play around with in the debug mode. I will just give it a free run, and I can see my LED